So the next section, 2.4, is about something called mathematical induction, and I'll explain what that is in just a few minutes. But here's the basic idea. Suppose we have some some propositional function, which I'm going to call S, with domain of discourse, um, the positive integers, lost a plus sign there, C plus. And we know two things. We know that S of 1, so when I plug in the smallest positive integer, I get a true statement. And I also know this next thing, which is a little bit more complicated. I know that if S of n is true, then if I plug in the next number, I'll also get a true statement. So that's S of n plus 1. And this works for any number, for any positive integer, n greater than or equal to 1. So I know these two things. What can we say then about the truth value of S of 2? What do you think? Based off of this information. Well, let's put these two ideas together. We know S of 1 is true. The second bullet point here tells me that if S of 1 is true, if I plug in the number 1, then S of 1 plus 1 is true. And S of 1 plus 1, that's S of 2, right? Okay, so S of 1 is 2. Now we know S of 2 is true. What about S of 3? What if I plug in the next number? Will this one be true? No one's willing to commit. Well, what if we just do the same thing? S of 2 is true. That means the next one is also true. So S of 2 plus 1, which is S of 3 that I'm asking you about, is also true. So this is starting to look like a pattern, right? So S of 4, we know that one's true because S of 3 is true. And if that one is true, then so is the next one. S of 3 plus 1, which is just S of 4. So this pattern will continue. If I go all the way to 100, just going through 2, 3, 4, 5, 6, 7, counting all the way up to 100, we'll have gotten to the point before it where we know that S of 99 is true. So S of 99 plus 1, which is the one I'm asking about here, is also true. And the pattern keeps on going. So what if we went way down the list, maybe into the billions or the trillions or higher? Will we ever get a number where we get a false? What do you think? What can we say about all of the truth values? Okay, yeah. So William, I am asking a little bit about what happens as n gets larger, as n goes to infinity. But what I'm really interested in is just whether our statement is going to be true or false. Right, it's always true. So if we just keep on going to the next statement, we start here, we go to the next one, go to the next one, go to the next one, go to the next one. Since the one before it is true, the next one is also true. And that pattern continues no matter how far you go. Since the one before it was true. Good. And this idea that we're talking about of using this sequence of true statements, this is the idea that's called the principle of mathematical induction. So it's a way in math of proving that an infinite number of things are true without actually having to prove an infinite number of things. Remember, we only started with two things. So if you can prove both of these statements are true, then for free, you get this whole sequence of true statements. Let me just finish writing out this word, principle of mathematical induction. And here at the bottom of the page, I've just written out, again, basically where we started with. Suppose that we have a propositional function S with domain of discourse Z plus. Looks like I dropped my my plus sign again. We suppose that S of 1 is true. And if S of n is true, then S of n plus 1 is true. And that works for any n we might want to plug in. Then our conclusion from the discussion up here is that S of n is always true, because we could just follow through that pattern, that sequence of true statements. So before we move on to trying to do an example, does anyone have any questions about this idea? So before we get to an actual proof using induction, first of all, let me tell you that condition one, the first bullet point that S of one is true, is usually called the basis step. And the second bullet point, condition two, is called the inductive step. And if we're going to use this idea of mathematical induction to prove a statement, we're going to have to organize it like this. We have to prove both the basis step, and then we'll prove the inductive step. So we will use these two steps, or these two conditions, to organize our proof. Because remember, if we can prove these two things, then we get for free that all of the other ones are true. Okay. So let's see if we can use this idea. Let's see if we can use induction to prove that the sum 1 plus 2 plus 3 all the way up to n is given by this formula, n times n plus 1 over 2. So what we're trying to do here is actually prove an infinite number of things without having to do all that work. We're trying to show that no matter what value here I plug in, this formula always works. But we don't have to actually do that. We don't actually have to prove an infinite number of things if we use this idea of induction. Okay, but before we get to actually proving the formula, let's just double check that this formula seems to work. So let's try it for some small values. Let's try plugging in 1, and then 2 and 3. So 1, I'm only summing one number, just 1. Is this going to be equal to 1 times 2 over 2? Does this work out? Anyone? Right. So the 2's just cancel, and you're left with the 1. What if I add 1 plus 2? Is this going to be equal to 2 times 3 over 2? Okay, so Davian says yes. Yeah, the 2's cancel again, leaving you with just 3, which is definitely 1 plus 2. Let's do another one, at least one more. What's 1 plus 3, or 1 plus 2 plus 3? Is this going to be equal to 3 times 4 over 2? So 3 times 4, that's 12. 12 divided by 2 is 6. And then on the left side, 1 plus 2 plus 3, that's also 6. So this checks out again. So if we stick with small numbers, it looks like our formula works. But the real question is here, does it work for any number? So if I plugged in some random number that I just picked out of a hat, will this formula work? Well, in order to show that, we have to use the mathematical induction in order to prove that the formula works, well, an infinite number of times for all numbers that you might add up. So let's organize our proof. So start by writing proof, just like before, and then tell the reader what you're going to use, what we're going to do. And in this case, we're going to do induction, so I'm going to say something like, we will proceed by induction. And to keep things a little bit more organized to help us see what's going on with our induction, I'm going to say that the sum of n things is equal to Sn. So S with a little n next to it is 1 plus 2 all the way up to n. So S of 1 would be this, S of 2 is this, S sub 3 is this, and so on. So to summarize, we're trying to show that Sn, the sum, is given by the formula, pointed to the wrong spot, n times n plus 1. It is very similar. So if you've taken calculus, you've probably seen things like this. Yeah, that's true. So this is similar to partial sums, I guess, is the calculus, the way calculus is related to this. So in calculus, you often think about infinite sums, and here we're thinking about finite sums, so partial sums. But if that doesn't ring a bell to you, don't worry about it, because we're learning all of this as we go. Okay, so after you write a little bit of a comment about what you're doing, what I like to do, and your textbook also does this, is to separate out the steps. Because remember, we have 2 steps that correspond to the 2 conditions from mathematical induction. The first one is the basis step, which is where we just have to show S of 1 is true. So in this case, we have to show that the formula works for the first sum, S sub 1. So let's just write that out. We must show that the formula works for S1. And when you plug in 1 here, we can write out all the details if we want. 1 times 1 plus 1 over 2, that's equal to 1. And that's actually all we have to do, because S1 really is just the number 1. We're done. Right. So what we're trying to do is show that the sum Sn is given by the formula. So we're trying to show Sn is equal to this. Okay, so you might want to say something about just a comment saying this is true, and we don't really have to show any work for this particular number. It's for free. And when you're working through these induction proofs on your homework, you'll see that the basis step is often fairly straightforward. You might not have to do much work at all, like in this problem. So the hard part is going to come in the inductive step. This is the part where you assume that S of n is true, and you try to show that the next one is also true. So we're assuming it works for S of n, the formula. And we have to show the next step. We have to show that S with little n plus 1, when you add the next term on, also obeys the same formula. But now we have to plug in n plus 1 where we had n before. So n becomes n plus 1, and n plus 1 becomes, well, we add an extra 1 on it, so n plus 2. So let's see if we can work it out. Let's do a little bit of calculation. So first we remind ourselves that Sn plus 1 is just the sum, 1 plus 2 plus 3 up to n, and then we also need the next term, n plus 1. But you might notice something here. When we write out this sum, the first collection of terms from 1 all the way up to n, that matches up with the previous sum, S sub n. So if we collect all of these together, 1 plus 2 plus 3 all the way up to plus n, this is actually just the same as S sub n. And by our assumption, we already know a formula for this term. So we're going to substitute in our assumption, what we know. Maybe I'll write a little note over here. So instead of writing out all of these numbers, I'm just going to write n times n plus 1 over 2. And then we have n plus 1 left over. So now what I have is a fraction plus something else. Let's combine those together. Let's simplify by getting a common denominator. Because we know the formula that we want in the end is a single fraction. So we're going to have to combine this into a single fraction if we ever want it to look like that, the conclusion that we actually want to draw. So this guy will have to multiply by 2 over 2 to get that 2 in the denominator. So our new total fraction is this, n times n plus 1. And then over here, we'll have 2 times n plus 1. And now the whole thing is over 2. We have a single fraction, but it still doesn't look like that. We'll have to use a little bit of algebra to rearrange things. So distribute, and then we'll combine terms again. We get an n squared plus n. Over here, we get a 2n and a 2. And we still have the 2 in the denominator. Now combine like terms. N plus 2n gives us a 3n. Now this factors. N squared plus 3n plus 2. That factors. And it factors this way, like what we wanted. N plus 1 times n plus 2. And then the denominator just follows along. So we started here, and we worked through using our substitution, what our assumption was, and then we used a little bit of algebra to get to the conclusion that we wanted. And since that's what we were hoping for, that's where we stop. And at this point, we've shown the inductive step, that's what we just did, and the basis step. So that means for free, using mathematical induction, we know that the formula works for anything that we might want to add up, any numbers that we might want to add up. 1, 2, 3, up to n. Any questions here? Looks like we're right at the end of class.